Hey everybody, welcome to our webinar. I'm going to do a brief introduction and then I will, Sebastian and Adrian will do the talks and we will open it up for Q&A at the end. If you have any questions along the way for clarification, feel free to put it in the chat and we ask you to stick to on-topic questions, please. This is being recorded and will be available on our YouTube within the next couple of days. A little bit about Data Umbrella. Data Umbrella is a community for underrepresented persons in data science, and we are a nonprofit organization. I'm a statistician by training, and you can find me on Twitter, LinkedIn, and GitHub at Reshama S. We have a code of conduct. We're dedicated to providing a harassment-free experience for everyone, and we want to thank you for helping to make this a welcoming, friendly, and professional community for all. So there are various ways that you can support Data Umbrella. The first and foremost is to follow our code of conduct. Another way is that you can join our Discord and ask and answer questions there and share any events with the community. The link to our Discord is on our website, which is dataumbrella.org. Another way that you can support Data Umbrella is to donate to our nonprofit. We are an open collective with Data Umbrella. And also if you work for a corporation that uses Benevity, what Benevity is a company match enabled platform. So you can donate through your company and typically your company will match, usually 50 to 100%. We have our YouTube channel where all of our webinars are placed. Subscribe to our YouTube channel to watch all of our other events, and I will share that link as well. We have a lot of playlists on YouTube. One of our popular ones is career advice. So if you are looking for a new career, check out our playlist. As well, we have playlists on contributing to open source, such as Core Python Pandas, Scikit-learn, PyNC. We have a bunch of webinars on NumPy, data visualization, and such. So we encourage you to check them out. We also have a monthly newsletter, and it's at dataumbrella.substack.com. We aim to get the newsletter out by the first of the month for our upcoming events. And we promise not to spam you. So 1 email a month from Substack. Our website has a lot of resources, particularly related to using inclusive language, allyship, accessibility, responsibility. And if you're interested in learning more, you can check it out at dataumbrella.org. We are on all social media platforms as Data Umbrella. Twitter and LinkedIn, we're quite active. Meetup is the place to go to join to find out about upcoming events. That's the first place that we place our event sign up. YouTube is for the videos. We have a blog as well, which is very nice, and the monthly newsletter. This webinar uses Big Marker platform, and we have live captioning. So if you go to the very top, there's CC for closed captioning, and you can select English is the most accurate language that's available. So if you'd like to see a live transcript, you can access it that way. I have a few community announcements for this webinar. The first is that we are seeking volunteers to help us with adding timestamps to our videos. And the list of videos is on our event transcripts repo on GitHub, and I will as well share a link to that. And so the reason we're doing timestamps is it makes it easier for viewers to get to the part of the video that they're interested in. And it also helps potential viewers find the video based on these search terms. And we really appreciate any help that the community can provide. And this is an example of, like a timestamp that was done recently for our GitHub Actions talk. We have our upcoming events. So on May 24th, we're having Contributing to SciPy. On June 7th, we're having Intro to Django. On June 14th, we're having a data visualization talk. And in July, we're having another PyTorch event. And that is, we don't have the date set yet, but if you're interested in PyTorch, that is definitely one to watch for. And the best way is to join our Meetup group and find it that way. Actually, the event is going to be on serving PyTorch models. So if that really interests you, then you might want to keep an eye out on Meetup. I also want to share an internship that has been posted by QuantSite on open source. And I'll share the link as well. And just to say for people who are watching this video later, today is May 10th, 2022. And so, you know, depending on when you watch this video, these applications may be open or not. They are looking for 8 interns over the period of July through September to work on open source. It's remote, so it is available to people, you know, outside of the United States. The start date is flexible. They're aiming for mid-June, maybe mid-July. The time commitment is flexible, maybe 25 to 40 hours a week, and there is compensation for this job listing, and I will share the link so you can get more information about it. So today's talk is going to be 2 parts with 2 speakers. The first one is Intro to PyTorch with Sebastian Raschka, and the second is Scaling PyTorch Code Using LightningLite with Adrian, and I should have asked how to pronounce your name, Wälchli. So yes. Today's speaker, I'll introduce Sebastian, is a machine learning and AI researcher with a strong passion for education. As lead AI educator at grid.ai, he is excited about making AI and deep learning more accessible and teaching people how to utilize AI and deep learning at scale. Sebastian is also an assistant professor of statistics at the University of Wisconsin/Madison and the author of the book Machine Learning with PyTorch and Scikit-learn. Feel free to tweet about our event. Our Twitter handle is @DataUmbrella, and you can find Sebastian on Twitter or RaspBT. I think a lot of you already know him because you found out about the event through him. And I'd next like to introduce Adrian. Adrian is a research engineer at grid.ai, developing and maintaining PyTorch Lightning. He graduated with a Bachelor of Science and Master in Science in Computer Science at the University of Bern in Switzerland. Prior to joining Grid in 2021, he worked for 3 years as a PhD student in the computer vision group at the Institute of Computer Science, University of Bern, under the supervision of Professor Dr. Paulo Ferraro. The topics he is passionate about are machine learning at scale, computer vision, computer graphics, and mathematics. And you can find Sebastian on Twitter at Adrian, WAELCHLI, as well. For this particular webinar, because Sebastian is an author of a quite popular book called Machine Learning with PyTorch and Scikit-learn, I will as well share the URL to this in the chat. We have 30% discount on this book. It's on Amazon, and the discount is good for a week or until, I believe, 75 people claim the discount. So it either expires May 18th or as the discounts are being used up. And with that, I'm going to turn the microphone and screen share over to Sebastian. I will turn off my mic, but I will be his. Oh, so in terms of slides, I will reshare the link to Sebastian's slides, and we will provide Adrian's slides after the webinar.
Yeah, thanks for the kind introduction, Reshama, and thanks everyone for joining. So let me see if I can share my screen so that we can see my slides. 1 second. I think here we are. I hope you can all see the slides now, or at least this purple slide. So yeah, today I'm excited to talk about PyTorch. It's something I use every day for my research and also for teaching. And you know, it's like 2022 where things have changed a little bit compared to how we did deep learning like 5 years ago or even longer ago. So there's this thing when I used to do research that I was usually training one model on a single GPU. Nowadays, to make things more efficient, even whether you use cloud resources or workstations or clusters at, let's say, your company, you may have access to multiple GPUs. So in the second part, Adrian will tell you how we take this PyTorch code and make it work on different devices, different hardware, and multiple, let's say, GPUs, TPUs, whatever you have. But if you have not used PyTorch before, let me tell you all about PyTorch, or at least the most interesting parts, because I think that's what we need to get started before we can scale our code. So in this talk, I mainly want to give you an introduction to PyTorch. I try to make it not too technical. There are a few interesting things about PyTorch. I think that Some of you may know, but also even if you have used PyTorch, in my experience, not everyone is aware of what PyTorch can do for you, basically. So what PyTorch actually is beyond, let's say, just being a deep learning library. So one thing PyTorch is really, it's a tensor library, and we will go into detail in a few moments what that means. So this is only one thing, though, that PyTorch is doing for us. So it's partly a tensor library, but then it's also an automatic differentiation engine. And what that means, I will also explain in a few moments. And lastly, as you may have heard about, it's a deep learning library. So PyTorch really is these three things: a tensor library, an automatic differentiation engine, and a deep learning library. And if you hear these three things now, you may wonder, okay, this sounds pretty much like TensorFlow. So yes, it is kind of like TensorFlow. I mean, PyTorch, similar to TensorFlow, is a library that allows you to do deep learning and other things. However, yeah, there must be a reason why people nowadays prefer PyTorch over TensorFlow. So this is a graphic I took from Papers with Codes. Papers with Code. And what they do is they look at papers on arXiv and look at, let's say, what library the research papers that do deep learning use. And what we can see here in red is basically like the trend, like that more and more people adopt PyTorch. So there must be a reason why this is growing compared to, let's say, other libraries. And personally, I used TensorFlow a long time ago. It was like in 2015 or 16. I used Theano, then jumped to TensorFlow. And then in 2017, 18, I started using PyTorch. And you might wonder, okay, if I used TensorFlow before, why do I use PyTorch now? I mean, this is kind of like partly a philosophical debate, but there are also some reasons personally for me that make it, let's say, more convenient. And I will tell you more about that later once I introduce PyTorch. But also I'm trying to say, okay, PyTorch is, let's say, not, I mean, it's different. It's maybe not better for everyone. So there's still maybe a reason why some people use TensorFlow and not everyone is using PyTorch. And also, I'm not saying you have to use PyTorch. I'm just trying to give you, let's say, some context why I personally prefer PyTorch. And after I gave you this introduction, I will then give you my personal reasons. So coming back to the topic that I mentioned earlier, PyTorch is a tensor library. So if you hear the word tensor, what does it actually mean? So there are, I would say, two broad definitions, or there's like the mathematical definition of a tensor. It's more like a mathematical object, but in, let's say, the computer science and coding contexts, usually a tensor library is something different. It's something we use more concretely, let's say, besides just mathematical manipulation of certain things. So a tensor library is essentially a generalization of certain concepts called a scalar, a vector, and a matrix. So a scalar is something called a rank 0 tensor. So a tensor is more like a general object, and then we can have different ranks. And here I'm giving you an example how we can create a rank 0 tensor or a scalar in PyTorch. And this is nothing different than, let's say, defining a float in Python. Here you can see I'm just assigning a float, the value 1. And this would be tensor in the context of PyTorch, a scalar, which is a tensor that doesn't, let's say, have a dimension. It's like this rank 0. But then we can also define a vector with 1 dimension or 1 axis, and this would be here an example of defining a vector, which is a rank 1 tensor, and then we can go further. We can define a rank 2 tensor, which is a matrix. So the difference now is that we have 2 axes, we have rows and columns and so forth, and we can keep playing this game, but then we run out of names. So we have the word scalar, we have the word vector, and we have the word matrix, but if we go further beyond that and add another dimension, there's no real name for that. But how you can think of this, let me go back one step. So if you think about the matrix here on the right-hand side, so this is something where we have rows and columns. Now, if you want to add another dimension, instead of having like this matrix, you want to make it a cube where you have another depth dimension, a third axis, you can actually think of it as a stack of matrices. And where we encounter that in the context of deep learning is when we work with images. So an image a color image consists of multiple color channels. And here, this would be an RGB image where we have a red, a green, and a blue color channel. And we don't really have a word for this, like scalar, vector, or matrix. So we usually call that a 3D tensor. However, sometimes people also just say in general, this is a tensor, but well, to be more precise, this would be a three-dimensional tensor, like we have 3 axes. And we can even play this game further and add another dimension to it. And in the deep learning context, for example, this would happen if you work with multiple images. So you have a batch of images or a stack of multiple color images. So you have yet another dimension. And in this case, this would be a rank 4 tensor, so a 4-dimensional tensor. So that's not super interesting here, what I'm showing you here, because it's just like setting up some data. But the point I wanted to get at is that a tensor library is essentially nothing else like an array library. A tensor library is essentially an array library. And you maybe are already familiar with arrays if you work with NumPy. So really, torch tensor is almost identical to NumPy arrays, how you use them. So you have the way you can construct these arrays or tensors, and there are also multiple operations like matrix multiplication, dot products, reshaping the array. It's essentially very, very similar to how NumPy works, and this is actually by design. When PyTorch started out, it was quite different from NumPy in terms of how the syntax worked, but then people requested so they asked the maintainers to make it more similar to NumPy so that they don't have to relearn certain things. So I remember, for example, back in the day, it was called dot size when you wanted to get the shape of the tensor. Nowadays, you can do dot size or dot shape to make it more, let's say, similar to NumPy. And okay, so why is that interesting now? So why would we use PyTorch instead of NumPy when we do deep learning? So one reason is that it has GPU support. So this is very nice because nowadays when you train big neural networks, it will be more efficient if you use a GPU due to the multiple processing capabilities of GPUs. So that is one thing that PyTorch has that NumPy doesn't have. But then, okay, on the other hand, there is something called QPy, where you can also have essentially NumPy on the GPU. However, another thing that PyTorch has, which NumPy doesn't have, is automatic differentiation support. And I will, in the next couple of slides, tell you what that means. I think this will be also very useful to you, even if you don't, let's say, use deep learning. This would be another nice thing to have, where you can use PyTorch also for other things, or even if you have a deep learning context, you can see that there is a little bit more control over it, how you, let's say, differentiate things. And then, of course, there's also the deep learning aspect that PyTorch has, where you have like these different pre-made functions and neural network layers that you can implement. But more about that later. So talking now about the aspect, the automatic differentiation engine, so what that means. So, so we just mentioned, okay, there is the concept of a tensor. What is, or how is the automatic differentiation useful? So here I'm showing you a model of a logistic regression classifier. This is a very abstract model. So what I'm showing you here is a logistic regression model where there's only one input variable, the x1 variable on the left, and there's one weight parameter, w1. So this is really just a very, very simple model that only takes one input feature. And then there is b for the bias unit. And in the center, this sum symbol and this sigma, the Greek symbol, they just symbolize what's going on internally. We will get to this in a few moments. And then the output here is like the y hat, which is like class membership probability. So this talk is not about a logistic regression, so no worries if that's a little bit abstract and let's say doesn't make sense right now. The point here is more about like how do we have, or how do we take a model like that and think about that more like computationally, and then also relate that back to automatic differentiation. So usually the main takeaway here is that there are inputs like x1 and there are outputs, and usually what we want to do is we want to change the weight parameters here, w1 and b, to get a desired output that is, let's say, close to a class label when we do classification. So personally, when I, let's say, think about automatic differentiation, I like to think about the model or the computation as a computation graph. And a computation graph is really, it's really like how the operations flow when you really execute the code. So if I go back 1 second, so if you look at this and then at this, what I'm showing you here is just a more detailed version of what I've showed you earlier. So there's nothing really new except that this is a little bit more detailed. And let me see if I can connect my iPad here actually, so I can draw on this. That would be maybe a little bit nicer instead of waving my hands here all the time. So I think it seems to work. So what we have here is as x1, that's the input feature, and then w1 is a weight parameter that we want to learn, and b is another parameter of the model that we want to learn. And let's say in this logistic regression context, what happens is we multiply these two together. And here I'm using a temporary variable. I call it u, and u represents this computation w1 times x1. And then we usually add the bias unit to it. And then we have another temporary variable, and we call that v. So v is essentially the sum of u and b here. And then from here, we go to the activation. We compute the activation, where we have an activation function sigma. And while I was making this slide, I was running out of space, which is why I didn't explicitly write out the activation function. But here at the bottom, this would be the logistic sigmoid function. So at the bottom, if you're interested, is how it is computed. Again, for this talk, it's not about logistic regression, so don't worry about these details. I'm more like trying to show you how we can, let's say, represent a model as a computation graph. And then in a deep learning context, usually what we would do is we compute the derivative of the loss with respect to the weights so that we can update the weights. Here, because of space reasons, I didn't include the loss function, but let's say part of this derivative is really computing the derivative of a with respect to w1. So it's essentially the derivative of the output with respect to the input weight. Another one would be b, but let's not worry about b now. Just looking at w1. The question in deep learning is always like, how can we change the weights of the model, the parameters, so that we get a desired output? So essentially, how can we change w that it affects a in a way that we want? So how do we make an update to w so that a changes in a way that it minimizes the loss? Part of it is this computation here at the top. And, you know, we can do this by hand. We can actually compute this without using PyTorch or TensorFlow or any toolkit that is out there. But it would be very tedious. How we do that is, personally, the easiest way is to break it up into multiple individual terms. So we can break this derivative up into 3 individual derivatives. Each one is shown here at the bottom. And in order to do that, I think it's very helpful to have this computation graph compared to just looking at a mathematical formula. If you look at the mathematical formula, I don't have it here, but it would be way more complicated to think about it. And I feel like this is the computation graph is a very easy approach to break this apart. And also, the other reason why I'm showing you this is PyTorch builds this computation graph in the background. It actually also uses the same concept. It's, of course, not visualizing it like that nicely, but when you run PyTorch, it will create this computation graph, and it will also compute these individual terms that I'm highlighting here. And then once you have them, there's some concept called the chain rule, where you can just combine them together, multiply them to get this derivative that you care about, essentially. So what's really nice here is using a computation graph, you can really see the individual terms you can compute and how to combine them together to get the desired output. And the reason why it's nice to break it up is that you can compute these derivatives individually. So you can really look at this one and only look at this one and derive or compute the derivatives like here, here, and here. So each of those is really just looking at one derivative at a time. And yeah, I'm not going over the details how I got these. That's like a topic, let's say, for another lecture. But let's say you computed these derivatives as shown here, then you can essentially combine them back, multiply them, and get the total derivative. And, this is a lot of work. I'm really showing you that it's a little bit tedious, as you may notice, because we have to think about it. We have to derive that. It's nice to look at, but it is not convenient, especially if you work with large neural networks. And I'm showing you that because I will show you in a few moments how we can do that automatically using PyTorch. So, but just, stay with me for a few more moments. So if we would then use at a concrete example where we have a network or a model that has the inputs as specified here. So we have a model input of 0.2, and we have the weight of 0.3 and the bias 0.1. If we would then carry out the computation in red here in these numbers here, I'm showing you what the actual values are that we would get when we run the model here with the parameters specified on the left-hand side. And then in PyTorch, this would look like as follows. So this is the manual approach, how we would compute this forward pass in PyTorch. So we would initialize our tensors here, or in this case, scalars. And then we have U, the multiplication, and then V, the addition. It's really just like what we see here at the top. And then we apply the logistic sigmoid function and then get the output here. So this is really how we would code up what we are seeing here in the computation graph. And then if we want to compute the derivative, if we derived everything manually, we can combine these individual terms, and then we get the derivative, in this case, derivative of the activation with respect to the weight W1, and it's 0.0497. But again, this is very tedious. I'm showing you a very simple model where it is possible to do it by hand. But if you think about, let's say, a complicated neural network, let's say a convolutional network, or even, let's say, a transformer network, this would be a lot of work if you have to do that for each individual layer and then multiply it all together. So what PyTorch allows us to do is it allows us to compute these derivatives automatically. So in PyTorch, there is this automatic differentiation engine called autograd. And there is, for example, this grad function. And this grad function allows you to do everything automatically that we have just seen. So the only thing you have to do is you have to define the computation that you want to do. And the variable that you care about, for that one, you have to say or specify requires a gradient equals to true. And then what you can do is you can use this grad function and say, I want to derive the activation with respect to weight W1. And then it will get exactly the same result that we got the tedious way here on the previous slide. So what's nice about PyTorch really is that it allows us to compute these complicated things automatically so that we don't have to worry about it at all. And it gets even nicer than that. Inside, when we use the layers in PyTorch, and also I will show you in a few moments, the backward function, it will do this automatically for us. So we don't even have to worry about calling this function ourselves. It will do it for us. The reason why I'm showing you this is you may be interested in an application where you want to compute derivatives like that. And I think this is useful to know, because I don't think everyone knows that PyTorch has this function. Okay, so we covered tensors, we covered automatic differentiation. Now let's get to the main part, the deep learning library. So PyTorch mainly is a deep learning library. The tensors and the automatic differentiation, they facilitate that because that allows us to run this or to run the code on a GPU and also have like the automatic, let's say, weight updates with automatic differentiation. Personally, when I code up a neural network, I would do it in 3 steps. I would first define the data set, like what data set I'm working with. Then I would define the model, and then I would define the training loop. So here really with the data set, I set up what is my data set, and that also defines what my input dimensions are for the different layers and so forth. And then based on that, I would set up the model, structure the model as it is, and then of course training the model to get, let's say, a good classification performance in a classification context. Since we don't want to make this talk infinitely long, in this talk I will skip the dataset part so that we only focus on the model and the training loop. But I will show you some code later that will include the dataset. It's just We are not going to explicitly discuss the dataset setup yet, because I think this would be a topic for another day. It would maybe take another, I don't know, maybe 20 minutes, half an hour. So, but if you have questions later on about that, I'm happy to chat more about that. And you will also see an example in the code. So, but then let's get to the part where we define the model. So usually how I prefer to define my model is using this sequential class here. So maybe going one step back and starting at the top, what we look at here is a convolutional neural network implemented in PyTorch. And really what you have to do is you create a class, which is essentially a Python class, and it has an init constructor, and there will be a few more things that I will show you in the next couple of slides. But here I'm really setting up the main layers of the network in the init. And this is really like the same init that you might encounter when you create a regular Python class. The only thing is we are inheriting from torch and end module, which has some additional things that, let's say, make the neural network work. Without going into too much detail, this is essentially just a little requirement that you add. And then with super here, you make sure that it uses also the setup, the init of this parent class. Then what I do here is I just save the number of classes, because that, let's say, determines my output dimension, but also later I may use that in other contexts. So I make that a class attribute so that I can access it also later. And then here in these boxes, in these blue boxes, I have the main parts, the main neural network implementation. Here I'm implementing a convolutional network. And this is not a requirement, but I usually separate the feature extraction part and the classification part. So the feature extraction part is really, in the convolutional network context, like the convolutional layers. So we have a few convolutional layers here, and in between we have max pooling layers, and then also the ReLU activation functions. And I dotted out the exact arguments, because otherwise it would be a little bit too long for the slides. But that's where you would specify, let's say, the kernel size, the padding, and the strides of the convolutions, and so forth. And I have a working code example that we can look at later. So if you want to actually run that, it has all these arguments. I'm just skipping them here, because otherwise it would be a little bit too cluttered. And so we have this sequential here, which will chain all of that together, which is very convenient, as you will see in a few moments. So then we can execute the network exactly like it is here. But of course, you also don't have to use sequential. I will show you also an example without sequential later. But personally, this is how I would set up the network 99.9% of the time. And then if these are my convolutional layers here at the bottom, we have classification layers, or in this case, only one classification layer, the output layer, a fully connected layer. So what we are doing here is we are first calling flatten. And this is because from the convolutional layers, images have color channels. And then when we run these convolutions, we usually keep growing the number of channels. So what we have here is we have usually data points that are three-dimensional. We have the channels times the height times the width. And these are like 3 dimensions, essentially. And fully connected layers, they only want 1 dimension, basically the number of features. And flatten will flatten it such that for one data point, this will only, so this will be combined into 1 feature dimension, essentially, and in order to make that work, essentially. So personally, I like to separate this out, the feature extraction and the classification, but you can also combine that together. So you could, for example, get rid of this parenthesis and then get rid of this and make this one large sequential call. It's just, for me, kind of like sometimes easier if I want to just look at the features that are extracted before calling the output layer. Okay, moving on. So this is what I showed you at the top here in the previous slide. This is really the setup. This is defining our network. And then at the bottom here, you see this forward method. And this forward method defines how we, let's say, use the neural network. It's defining the computation. If we get a single data point x here, it's defining how we process the data point using our layers. So since we used sequential, it's actually incredibly easy. We just have to call features, which is our features here. We just have to call features on our input, and then we will get the extracted feature. I just named them X here too, just for efficiency. So it's kind of overwriting the variable that can save some memory. You can give it a different name though. You can call it, I don't know, features or whatever you like. And then on these features, we call the classifier part, which is in this case just to flatten in the output layer. And then we get back this X and return it. And this is really it. The sequential will make sure everything gets executed in the right order, which is nice. So this is all we need to set up our convolutional network. So just to highlight again, we have sequential, which defines the order of how the layers get executed. And then in the forward method, we actually execute. And the same then is true for the output layer. So you can also have, by the way, multiple output layers here. I think in the code example, I have 2 or 3, not multiple output layers, but multiple fully connected layers. So in the code example, I will have also multiple ones because sometimes it can help with improving the performance. One little note about that. So I showed you how to use sequential, but you may have some special, let's say, requirements for your model if you, let's say, don't do classification or you want to do some custom manipulation. So in this case, PyTorch is actually very flexible and it allows you to put together the forward method however you like. So here what I'm showing you is the same network, exactly the same network, just implemented a little bit differently so that I only have, let's say, the layers that have weights and biases here in the init method. And there are also, for example, functional methods for pooling and ReLU here. So it's essentially just a slightly different way of implementing it, but it's doing exactly the same thing. And why I'm showing you this is it's basically showing you that there is a little bit more flexibility how you put together the forward method. And you don't need to use sequential. You can mix and match everything. Personally, I prefer to use sequential for my networks if it's a classification network, a regular one, because then I don't have to think about putting everything into the right order. Because here now, I have to think about, okay, I have to give this the name conf1, and I have to use conf1 here first, and then conf2 too. And if you do it like that, I would say it's sometimes more prone to making typos that you maybe do a copy and paste, and this is also a 1 here or something like that. And sometimes typos can happen that you have things in the wrong order, which is personally why I prefer sequential. But sometimes you need maybe a little bit more flexibility. So in that case, you can consider modifying your forward method a little bit more. But yeah, that is the model that I wanted to show you. So this is how we set up neural network. In the second step here, now the interesting part, how do we train the neural network? So how do we define the training loop? So first, a few setup steps. So we would first initialize the model and the optimizer. So in the previous slides, I showed you how to define a class, but now, we have to use the class to make essentially an object that we can then train. Here I'm providing the number of classes because it determines the number of output nodes. So if I have something like, let's say, MNIST, I have 10 handwritten digit types. So I would have 10 output classes, for example. So I need 10 output nodes. Here's an optional step, model to device. And what it is doing is it can move the model, for example, onto a GPU. If I say, if I define device as, if I define device as, let's say, CUDA, it would move that to a GPU that has CUDA support. But then it doesn't have to be, let's say, a GPU. It could be a TPU, and Adrian will talk more about that in his portion of the talk. But I'm just showing you here, if you want to, you can move the model to a GPU. And this is recommended if you train, let's say, a convolutional network or any bigger networks. For fully connected networks like multi-layer perceptron, it might be fine to train it on a CPU if it's relatively small, especially if you have, let's say, a computer like with ARM processors, like the MacBooks, they are pretty fast. So sometimes I'm lazy, and for teaching, I want to just train a simple multi-layer perceptron. I sometimes just train it on my laptop to save time, let's say using a different machine with GPUs. Okay, so now assume we have initialized the model. One other thing that we need is initializing the optimizer. So this is, for example, defining how we train the network using the learning algorithm, for example, stochastic gradient descent. Personally, I like using Adam, which is kind of like a modified version of stochastic gradient descent, which has an adaptive part to it and also a momentum term. It usually, personally, I find it requires less tuning. So finding a good learning rate is usually easier. It doesn't mean it's always, let's say, the best optimizer, but it's usually working well out of the box with a learning rate like 0.005 or something like that. It requires less tuning. The more interesting or the key part here, though, is that we have to specify what the weights are that the optimizer should update. Here, we are using model.parameters. So .parameters will automatically take care of extracting all the learnable parameters from the model. So if I go a few slides back, go to this one maybe, one of the benefits of using torch and module is that it will automatically take care of everything, and everything that has parameters like conv2d here and the linear layer, this will be then accessible via model.parameters. So we don't have to manually specify which layers we want to train. If we call model.parameters, it will automatically take care of that, and it will update all the learnable parameters of the network. So, okay, we have our model, we have our optimizer here. Next is really the core training step where we iterate over the training examples. So usually we train our model over a couple of epochs. So we specify a number of epochs. It really depends, of course, on the data set and the model. But let's say this could be a number between 10 and 200. Then what we do is a good practice is using model.train. And this puts the model into a training mode. For example, some layers like dropout or batch norm, they behave differently during training and inference when you use your model on new data. So here, just to make sure your model is in training mode, I always include that at the beginning of each epoch. And then we iterate over the individual batches, the mini batches here. And we haven't talked about the train loader. We will see that briefly in the code example. So there's a train loader in PyTorch that lets us conveniently extract the batches from the train loader for each epoch. And if you put the model onto a device here, there's one little thing you have to make sure that the features and the targets are also on that same device. So it wouldn't work if, let's say, the model is on the CPU and the features are on the GPU, or the other way around, if the model is on the GPU, but the features are on the CPU. So just to make sure they are on the same device, you would add this to device here to ensure the model and the features and the targets here, the class labels, would be on the same device. Okay, so we have now iterated over the mini batches, or we are still iterating over the mini batches. But to zoom in, what happens when we are iterating over the mini batches? There is the forward pass. The forward pass will essentially look like that, where you just call model features, and this will execute the forward method that we have defined when we set up our PyTorch class, or PyTorch CNN class. And this will essentially extract the features and then run this through the classification layers, the output layer, and get our outputs. And then we feed these outputs here to the loss function. Here we are using a cross-entropy loss function, which is something we can use for classification. For example, if we have a multi-class classification problem, we would use the cross-entropy loss here, together with the targets, where the targets are really the true class labels. So one thing worth highlighting is that we feed it the logits, which is the unscaled outputs. It's not the, if you have heard of it, it's not the sigmoid or softmax activations. So really here you want unscaled values. You don't want probabilities, because the cross entropy loss, it internally uses the log softmax to convert this into, let's say, log probability scores. And in this case, it's kind of like important to remember that we feed it the logits. It's a little bit unclear sometimes from the documentation in PyTorch, so it's a common mistake to give it, let's say, sigmoid or softmax probabilities, and then you might get weird results. That's why I'm highlighting it here. And for the targets here, the targets are integers. So if you have mnist, where you have 10 different class labels, these would be integers between 0 and 9. So really just integers 0, 1, 2, 3. So for the different class labels, not one-hot encoded class labels. So cross entropy already takes care of the one-hot encoding internally, so we don't have to worry about one-hot encoding ourselves. It's really just like the integer class labels. Okay, so this would be the forward pass where we get our logits and then we compute the loss. But now the part is really, how do we learn? How do we update the network? And that is where the back propagation or backward pass comes in. So there are two main steps, or there's one additional step I will show you in a moment. But one is essentially calling zero grad on the optimizer and then calling backward. So why do we do that? So zero grad is really to make sure that the gradients in each iteration are reset, because technically it's possible to run two forward passes and then do something like a double backpropagation or something like, or you can do a double backpropagation, but you can also accumulate the gradients by calling the forward pass 2 times. But most of the time we don't want to do that. We just want to do one forward pass, a backward pass, forward pass, backward pass. So in this case, we have to do the zero grad to reset the gradients of the previous run to 0. And then we call one step here, and then we call backward. And in backward, we are essentially applying, or we are computing essentially the gradients of the current pass. So zero grad is resetting the gradients, and backward is computing the gradients. It's essentially what I showed you manually in the computation graph examples when we call the grad function. So that's doing something similar internally. It's using the grad function in PyTorch to compute the gradients. And then in step here, this will apply the gradients to the weights. So it will essentially update the weights. So the optimizer here will update the weights. And this is essentially it. So here, really, we have multiple steps. We have the forward pass, which computes the outputs of the network. Then we have the backward pass, which computes the gradients. And then we update the weights with the gradients. Okay, sorry. Next, we have the evaluation steps. And this is really something optional. So here, it's just so that we can keep track of the performance of the network. I have some optional evaluation steps. And for that, I put the model into evaluation mode, which is important, for example, if you do something like dropout. Here in our network, it doesn't really matter, but I think it's a good practice to always include that, because if the network has dropout, we don't want to randomly drop nodes when we evaluate our model on a validation or test set, because we really want deterministic behavior in that case. Another thing worth highlighting is, that's essentially what I was saying, we want to use training and evaluation. But another thing worth highlighting is using no grad. And this one really says we don't care about gradients. We don't need to compute or construct the computation graph. Because otherwise, if we don't do that, PyTorch will always construct this computation graph that I showed you in the computation graph section. And if we don't need it, it would be computationally wasteful to do that. And for computing the accuracy, for example, we don't need computation graphs for the backward propagation, because here we don't update the weights. We are just evaluating the model. And it would be kind of wasteful to build this computation graph. So here with torch no grad, we say, don't build the computation graph for us, because we really don't need this here. And yeah, this is in a nutshell how the training loop works in PyTorch. Coming back maybe to a question I had, like that I phrased earlier. Why do I like PyTorch? Because, I mean, well, PyTorch is, if you used it for a bit, it becomes relatively intuitive. I mean, there were a couple of steps that I showed you. It looks a little bit complicated, but you can actually get quickly used to it. And what's actually nice is, personally, I think it's very Pythonic. So the way you write the code looks very Pythonic, which is a saying to say it, well, it adheres to the Python concepts of making code look proper or nice. But at the same time, it's also very flexible. And this is very useful if you want to change certain things about the network that is a little bit out of the box. So if you do research, for example, you take an existing network and you make some changes to it. And in PyTorch, it's incredibly easy. So in a research project, I had to define a custom layer once. So where I just defined my custom layer. I won't go over the details here, but it's basically how it looked like. I mean, it's still a little bit complicated. It's a couple of lines of code. But then there was someone who ported this layer into, let's say, Keras to run it in TensorFlow. And you can see here on the right-hand side, it's way more code. So if I go back, if I compare this one to this one, you can see PyTorch is actually a little bit easier to use. It's shorter and more concise. And personally, I feel like this is very valuable when you work on a research project where you really you want to make the changes as convenient as possible. You want to, let's say, iterate quickly. You want to try out new ideas quickly. And the fewer things I have to worry about, the more, let's say, easy it is to do research in that manner where you can make modifications quickly. So I wanted to show you also a live demo. I think it took a little bit longer than I expected, but let me just briefly run a live demo. And also I should mention, or if you're interested in more details about PyTorch, in my book, there are a few more details. In this talk, I mainly focused on the main takeaways so that, let's say, you have a minimal working example of how to use PyTorch. But of course, there's always more to learn. So if you're interested, there are some more details in the book. I also wanted to mention we have a developer conference coming up, PyTorch Lightning developer conference in New York on June 16th. I think there are still some spots available. If you're in New York, it's free to attend. Also, we will have virtual portions. I think if you go there, it will give you some more details, just in case you're interested. We will have some really, really cool things to announce. And we also have workshops there if you're interested in that. So yeah, with that, let me go to the live demo. And I think someone hopefully posted the link in the chat by now. But if you want to run these code examples later, they are all on GitHub, so under this link here. And I think there's also, just before the talk, I added a link to the slides. You should also be able to download the slides from there if you want to, let's say, look at them again. But let me see if I can share my browser, so I can share you actually can show you the code example. 1 second. I'm not seeing it right here. Somehow it does not come up. Oh, 1 second. There we go. So just using a Jupyter Notebook. That's the right one. Let me make this also bigger once loaded. Okay. I think this was it. Yeah. Don't know why it's called untitled, but okay. And so here in this example, I'm walking you through the code that I just showed you. It's a little bit more detailed than what I showed you in the talk. There are a few extra things where I have certain settings here, where I'm defining a random seed for reproducibility, a learning rate, the number of epochs, the batch size, and the number of classes. And here we are using MNIST. So there is actually an MNIST dataset implemented in PyTorch. However, I set it up like this so that it mimics any image dataset that you might work with. So it's essentially here the PNG files of MNIST that I uploaded to my GitHub. And you can think of this really as any dataset on your computer, basically. Yeah. And we skipped over this due to time reasons. You can maybe notice it's already an hour. And if we talk about data sets, it would be maybe another half an hour. And I really want Adrian to show you how to scale code. So we didn't really talk about the data sets here. But here's an example, basically, how we can put together custom data transformations. You can really do also random augmentation and normalization, whatever you like. Here, it's just very simple, converting an image to a tensor, which will actually scale the pixel values to 0 and 1. Here, what I'm now doing is I'm splitting the training set into a training and a validation set. And we also have a separate test set. And yeah, again, the code, you can maybe look at this later. And if you have any questions, I'm happy to chat about this more. It's just like I don't want to, let's say, take too much of the time so that Adrian also has a chance to show you how to scale code. But let's assume we have set up our data loaders. You can take a look at the images here. That's how they look like. So this is like 8 by 8 images. I'm just showing you multiple ones. So here we have one batch of 64 images arranged in an 8 by 8 grid. Just to look at the images to make sure they look okay. It's always, I think, helpful in practice if you have a data set to make sure the data is loaded correctly. Now, here I'm showing you now the network that I showed you on the slides. And as you can see, there are a few more details with the channels and the stride that I filled in. But essentially, it's the same network, except it's a little bit longer. I added another fully connected layer here to improve the performance. So let's initialize that. There's a compute accuracy function, which maybe I will skip over. But if you have questions, happy to chat more. And here is the training block that I showed you also on the slides, where we really just have these major steps, cross entropy loss, backpropagation, and the updates. Some logging to log the performance. It's a little bit more detailed. I'm also looking at the training accuracy. I find it always helpful to make sure the model is not overfitting. So I'm just running this now, and it should print an output every 100 epochs here, batches, every 100 batches. And yeah, it's pretty quick, so it's training. Usually what I do is when I train network, I want to see that the loss goes down. It's not always the case because it's stochastic gradient descent. Sometimes it's fluctuating, but overall it should go down, and it's already pretty good accuracy, 96%. It's actually also not overfitting very much here. It's 96 and 96, which is pretty good. And this would now continue training maybe for a few minutes, and then we would look at the test accuracy. But you can see this improves already. So that's good. And I think with that, I would pass it on to Adrian. And after Adrian's section, we should probably have some minutes, maybe 5 to 10 minutes. I'm flexible for questions by the audience. Happy to chat about pretty much everything, but let me hand it off now to Adrian so that he can show you how we can scale that up to multiple GPUs. So this is training on one GPU. It's quite quick because it's just the MNIST dataset, but in the real world, you may have something that is a little bit bigger than MNIST. So Adrian will show you how we, let's say, train networks efficiently using multiple GPUs and other devices. So let me then stop talking and let Adrian take the stage here and tell you all about scaling the code to multiple GPUs.
Yeah, awesome. Thank you so much, Sebastian. So just give me 1 second to switch to the screen here, to my presentation.